So in the previous section, we solved for expression 1. Let's continue our journey to solve now for expression 2, which is part of the weight update equation. And this is our equation number 5. And let's go back to our expression 2, this one. So we copy this whole thing. And we paste it here. So remember, this is our expression 2 that we are now solving. And here again, we will do some manipulations. So what manipulations can we do here? So we can take advantage of the fact that the desired signal can be expressed in terms of error. And how is that done? Is that, so from our discussion earlier, if you remember, we had said that our error, ek plus 1, is nothing but the difference between the desired signal and the output of the filter. And this again is nothing but, so we're talking about the recursive form of weight. So this is equivalent to weight at time point n getting multiplied by the data point or the input at time n plus 1. So now we find the expression for dk plus 1, which is ek plus 1 plus wn x n plus 1. This is a very important expression. And as you can see, we can take this and replace it in the above equation. So we can write x n plus 1, which is this term, multiplied by e k plus 1 plus wn x n plus 1 divided by this denominator. So now I'm going to open this bracket here, this bracket, and try to do some more manipulations. So I can see that my first expression is wn xn1 plus square, and my second expression is ek plus 1 x n plus 1. And I'm going to be dividing both these sub-expressions with the same denominator. So, or rather I can just keep it like that and do this. Right, so once again, we will do some more manipulations to this expression, and what we can do now is split again these two parts and write them like this. So here it is wn, and again I will do a minor manipulation here. I will write this as the square part like this, and the entire denominator goes here, plus this part, and the entire denominator goes here. Now this manipulation has allowed me to do something, which is, if you see this part, this is exactly k n plus 1. So if you see, this is how k n plus 1 was defined, and we have manipulated the whole expression to form kn. So this becomes kn x n plus 1 multiplied by wn and here again you see this is nothing but k n plus 1. So we again get k n plus 1 e k plus 1. So this is my expression 2. So now I'm going to add my expression 1 with expression 2 and see, actually the denominator will not survive because this denominator is part of k n plus 1, so this won't be there. This is how my expression 2 will look like. And now, so let me just write my expression 2, which is kn xn plus 1 wn plus k n plus 1. This is my expression 2, and to it I have to add expression 1, which was here, if you see. So 1 minus kn plus 1 xn plus 1 wn. Remember, this whole thing is wn plus 1. So we will, this term is common between these two expressions. This is n plus 1. So what will happen here is, these two terms are common, I'll take it out. So what I'm left with, k n plus 1 x n plus 1 plus k n plus 1 x n plus 1 wn plus k n plus 1 with the other term. As you can clearly see, these two terms, they cancel out. And what we finally get is a very beautiful form of weight update equation, which says the new weight is equal to the old weight plus some kind of a gain multiplied by the error term. So this is exactly what we were looking for. We have converted the weight update into a recursive form. Remember here, k n plus 1 was nothing but x n plus 1 divided by and this is what is called as gain. So this is gain, this is error, this is the old weight, and this is the new weight. And this entire equation is called the weight update equation. Moving forward, now we will do some more manipulations. In particular, we will talk about a variable called pk, and this is expressed like this. So if you see that in a lot of places this term is appearing, which is basically autocorrelation of the input signal. So we will define a term called pk, which is going to be the inverse of covariance matrix, and this is defined like this. So if this is what is pk, then pk plus 1 will be nothing but the terms going up to n plus 1 xk square, and in terms of recursion we can redefine this as k going from 1 to n xk square, and then xn plus 1 square, the n plus 1th term. Now as you can see here, this is nothing but 1 by pk. So we will substitute this. Essentially we are trying to make this in recursive form. So what will happen now is 1 by pk plus, and we further simplify it. So this will become 1 plus pk. So this is a very important formula, which is talking about how to find the value of p at time k plus 1 from its old value at time k. We can further simplify this. To do so, what we can do is that, let me write it here. Pk plus 1 is nothing but, let's do some manipulation here, and that manipulation is, I'm going to multiply this with since I have multiplied by this, so I have a term pk which was already existing in the numerator here, but there's an extra term which has come here, so I must subtract this extra term. That's what this manipulation is all about. So that extra term is pk square x square n plus 1 divided by the same denominator. So this little manipulation, if we solve this equation, we go back to the equation shown above. And why I have done this is, if you have a look at this now, both these terms, they cancel out. And what we get is pk minus pk square x square n plus 1 1 plus pk x square n plus 1 pk plus 1. Why this expression is so important? So let's analyze each term. What this is new data point that has become available in the time series. This pk is the old inverse covariance factor. Basically, it has come from autocorrelation of the input signal, and all other places where this pk is appearing is the older version, which is used to derive the newer version here. This is new pk at time step k plus 1. So this whole thing is called update step for inverse covariance when we talk about the matrix form of this filter. So having done that, now the only thing that remains is that we have to find a recursive form of the gain equation. Remember kn plus 1. And what was kn plus 1? It was given here. Here. So let's derive the recursive form of this equation. Kn plus 1 is nothing but xn plus 1, k going from 1 to n, xn xk square plus, now if you see carefully, this is nothing but 1 by pk. So we will rewrite this whole equation, x n plus 1 1 by pk plus x square n plus 1, and we take this on top. So this becomes the recursive form of the gain update. So once again, this is new data to the filter, new data point. This is old covariance, inverse covariance. And this step helps us in calculating the new gain. So we have three equations. We have weight update equation, we have inverse covariance update equation, and we have gain update equation. So in the next section, we'll summarize the results.